Hi, everyone. Thanks for joining. We're just going to take another minute to allow everyone to get in here. Thanks again for joining. Talk to you in 1 minute. Alrighty. Hello, everyone. Thank you for joining this session today. It's part one of a series on vacuum system design and installation. This first installment being an overview of best practices, specific aspects of operating chemical processes under vacuum. My name is Matt Murray. I work for the Marketing Communications Department at Edwards, North America. We're going to get started in just a second, but I did want to take a moment to note a couple of things. First being, as mentioned, this is the first of 3 webinars we'll be giving. If you haven't signed up for the next in the series, you will receive a reminder with a link later this afternoon to sign up for those. And below here, I've shown the link for that where you can register. Keep in mind, we will have a question section. We're going to be about just under 30 minutes for the presentation, and we'll allow 15 minutes for questions at the conclusion. And you can enter any questions into the question box in the GoToWebinar panel there. So now I would like to hand this over to your presenter today, ANDREAS KOBUS. ANDREAS has over 22 years of experience with vacuum technology for the chemical industry, and he's held positions from systems and applications engineer to sales and business development. ANDREAS is currently the business development manager for the process and steel markets here at Edwards. So with no further ado, ANDREAS, please take it away when you're ready.
Thank you, Matt. Thank you, Nicole. Give me 1 second to get the presentation started and good. Ready and set to go. I hope you can all see my screen and hear me okay. Hello and welcome to this webinar from my side as well. Let's get started right away with the specific aspects for the vacuum technology for the chemical industry. This first section is solely about production efficiency under vacuum, which factors are driving it. Again, I will refer to the other 2 seminars following and have a deeper dive. So this will be solely about production efficiency and best practices, things that we saw in the long experience Edwards has with this industry. So let's get started with this, because that's typically what you see when you get into your vacuum training, right? Vacuum technology is all about the gas state, and it's following the gas laws. So what you see is on the left, typically it's a piston pump or a moving piston in a cylinder to show the the most frequent and just derivative from the ideal gas flow. It's pressure times volume is constant. What it means is if you're solely in the gas state, like looking on the left with the piston up and the gas, basically pure gas enclosed in that chamber, assuming it has a certain constant mass and temperature, that has a certain volume, and assuming that volume is under atmospheric conditions, 760 torr, that's what the pressure gauge illustrates here. If you move to the right, if you move the piston down, means you, in this case, quadruple the volume of that mass in that cylinder. You basically have cut the pressure into 1/4 what it was before. I'll show you that first because it's pretty straightforward as long as you look at just the gas state. And it's the fundamental difference between standard cubic feet and actual cubic feet. So standard cubic feet is obviously standard conditions, atmospheric conditions, constant mass and temperature. The actual cubic feet in this case, and just in this simple case, is actually 4 times the standard cubic feet, obviously. That's very straightforward, and that's what usually vacuum is being taught about. In distillation and drying processes, that's a whole different game. So for the chemical industry, we felt the need to go basically hold this seminar specifically for these kind of processes. And I'm going to focus on drying and distillations and on those similarities, well knowing that both processes are pretty different. But what is important is we now have a multitude of different agents and different states, means phases. In both cases, drying and distillations, you have a liquid phase present and a vapor phase present. And that simple fact changes the entire game. It's not as simple anymore. It's not as straightforward anymore. And the reason for that, and I will change to a much simpler looking diagram. I just wanted to show you the sole reason for that is just simply the phase diagram of any agent. This is in that case the phase diagram of water. And the point is, well, it's actually driving the entire business in distillation and drying under vacuum. This is why this industry needs vacuum pumps in order to influence the boiling point of a certain agent to boil it off at lower temperatures than they would under atmospheric conditions. The point here is these phase diagrams exist for every agent, and what's telling you is in which state an agent is solely determined by temperature and pressure. That's all. So let's move on to a simplified diagram of the state diagram, and let's forget about the solid state for a moment. It's about liquids and vapor. So I marked the vapor state in yellow and the liquid state in blue. Again, it's on the vertical axis, it's pressure. On the horizontal axis, it's temperature in any kind of dimension. It doesn't matter here. And for the state or for the case that you only have, or we only have a vapor state, pressure and temperature can be moved independently, and they follow the gas laws, and they follow pressure times volume is constant, as I've shown you in this piston pump example. The whole game changes if you have a liquid present, which is the very definition of a drying or a distillation process. So what happens if you have the same agent present in a liquid state and in a vapor state is these pressure and temperature are now moving in lockstep. So that means if the liquid phase has a certain temperature, the pressure of the vapor phase above that liquid phase is determined. You cannot change it. It's set. It's called the vapor pressure. And you can only move these two parameters, pressure and temperature, along the phase line between liquid and vapor state. So it follows the phase diagram. So what does that mean? Let's look into a reactor illustrated here on the left side. The reactor has a liquid phase at the temperature T2, which means the vapor phase has a pressure P2. And imagine this reactor is sealed off, nothing else in it than one single agent, let's say it's water, in liquid state and gas state. So your pressure P2 is defined by the temperature of the liquid along the phase line, along this lock, and it's lockstep. So in this case, if it's water, you see with P2, if it's a single agent, you see the vapor pressure. If you put a gauge in, like shown here, you see the vapor pressure of water at the temperature T2. Okay. So the next step is to say, okay, let's make it a distillation or make it a drying process. In this case, it doesn't matter. It doesn't make a huge difference. So to make it a process, what's being applied is vacuum capacity on the vapor side in an actual cubic feet per minute, and heating power on the liquid side. So we start, and that's what's driving it. And what's the outcome of that driver? Which, to be clear, the driver is the heating power that we apply to the liquid, is an evaporation rate, and that evaporation rate is driven by the heating power and it's supported by the vacuum capacity, and it comes off the reactor in a mass flow in pounds per hour. In order for the mass flow, for the mass to change the phase from liquid to vapor, that takes energy, and it borrows the energy from the liquid state. So just to be clear, if we wouldn't apply heating power, just the vacuum capacity going, what would happen is that, again, the pressure in the reactor is determined by the temperature of the liquid. So what would happen is there is an evaporation rate. The vacuum pump would drive this, but it would borrow energy to do that from the liquid, which means temperature 2 goes down. You cool the system down. And the heating power is to prevent that from happening. You want to have a stable temperature under which you want to distill this fraction, the liquid. You want to turn the liquid into the vapor state at a certain defined temperature. So you can see already where this is going. Where this is going is the vacuum capacity in ACFM has a relation and is basically in harmony with the heating power that generates an evaporation rate. And I'll get back to this, but I wanted to explain the effect first. It's highly important for the chemical processes like distillation and drying to understand where the effects are coming from, that you can see later. What that also means is, as long as your pump is not too small, which means your vacuum that you apply, if it would be too small, which means it is less ACFM than the heating power generated in pound per hour, you would overheat your product. The temperature 2 would go up, which, since everybody in this process, in this industry, wants to avoid that, it's deteriorating eventually the product. There's a reason why you want to have a temperature at a certain range in the liquid. That is the one thing. So, but that drives the vacuum capacity mostly being too high, because everybody is concerned that too less capacity would mean you slow the process down. What that means is, if you have too much capacity, that the vacuum pump is basically just imbalancing the process to the other side of the pendulum. So you have so much evaporation rate that the heating power can't keep up with it, and the temperature in the liquid would go down, which I've seen processes slowing down by that significantly. So that's just an interrelation that I want you to make you aware here. It's important because the production efficiency is highly dependent on the balance between what you put in actual CFM and in heating power. The other aspect before we go into best practices is the role of a condenser in this process. And it has to do with the exact same interrelation in the phase diagram distillation is constantly about two phases, liquid and vapor. And since it's defined by its temperature and pressure, and it is in lockstep, it is important to understand what's going on here. So let's assume we have a temperature T1 in the liquid in the reactor, apply heating power, generating a certain evaporation rate. And the heat exchanger typically has a cooling water at T2, which is lower than T1. So what is this condenser doing? It actually, since the vapor leaves the reactor, the condenser takes the vapor out and puts it back into the liquid state, which means in that moment, it is not anymore relevant for the vacuum process. It's back into being a liquid. And that makes a condenser a vacuum pump. Very simple. And if you think that process for a moment with me, this is where I put a gauge on the end of the condenser on the vapor side. That condenser pulls a vacuum. And if you don't have a leak rate, let's go for a moment into this theoretical sense. I know we always have a leak rate, but theoretically, if there wouldn't be a leak rate, you wouldn't need a mechanical vacuum pump. Your condenser is doing everything, and it's doing everything right. Because the temperature T2 is lower than T1, which means the pressure above the surface of the liquid on the condenser is lower. It's now going, that pressure is lower, and therefore it pulls gas, it pulls vapor out of the reactor, condenses it, and the capacity of your condenser is the liquid drain mass flow, the drained mass flow, and you can calculate it always in its volumetric equivalent. Mass flow and volumetric equivalence is determined, and in the second seminar we're going to learn on the engineering basics how to calculate that. So the important point is a condenser is a vacuum pump, and that it doesn't really matter if it's a batch process or a continuous process. In this phase, while you have this phase going, you have massive vapor loads evaporated and condensed in your condenser. Your mechanical vacuum pump is still needed, but it's basically only needed to take the non-condensables, your leak rate basically out. The rest is done by a condenser, and it has an almost infinite capacity to your process, as long as it drains and condenses liquid. So why is that important for production? So in order to answer that question, we need to look into what delays the production time. So if you look at this, related the reactor, the condenser, and the vacuum pump, and in this time the control valve already in it. What delays your production is an imbalance between your vacuum capacity and your heating power. Again, it's usually oversized for various reasons. But if you apply too much vacuum during the running distillation and basically take more evaporation out than the heating power supports, the temperature in your reactor goes down. That process can freeze off the entire surface of your liquid. It just freezes it off. The tricky thing is your gauge in your reactor still shows the pressure is going down. Everything looks great, but it isn't. It is basically the reason why the pressure is going down is not because you have such a massive vacuum pump going. The reason can only be you cool down the temperature of your liquid in your reactor and eventually even freeze it, because the evaporation rate is just on the surface of the reactor. I've seen drying processes freezing down, which means the pressure in the dryer looks great. The drying good, the product comes out of the dryer and it's frozen. It's a frozen block. It's not dried at all. It's just, and you can imagine how long such a process takes, and the result is just unsatisfactory. So the reason for that is, keep in mind, vacuum pump, ACFM, and heating power are interrelated. The other best practices that I want to make you aware of: hydraulic locks in pipeworks, remaining liquids in your drain tanks, liquid carryover in the vacuum pump, and capacity loss and pressure loss. There, except for the latter, They are all interrelated and have to do with what I was trying to explain to you over what a liquid and vapor state, what the presence of both states means in a distillation or drying process. So let's go into some best practices and details. First of all, and first and foremost, the importance of vacuum controls. So what I've shown you is, again, the reactor with the explained interleak to the vacuum system. And the diagram here is a capacity pressure diagram. In this case, it's double logarithmic scale. It doesn't matter except for the ease of showing what's going on. So I picked the performance curve just randomly of a vacuum pump. In this case, it's an Edwards EDS 300 dry pump. It's a 160 ACFM pump. So you see that 160 ACFM in the yellow curve that goes from the right to the left all the way through all the pressure gauges. So a vacuum pump is a volumetric machine. It has basically a constant volumetric capacity over a wide range of pressure. Okay. So instantly enough, your mass flow, and keep in mind that's your evaporation rate, your mass flow coming off. It's driven by your heating power. The mass flow, the equivalent volume pressure relation of a mass flow in this kind of diagram is a straight line, shown here in blue. It's just going from right to left and just going up. Okay. So the point where the mass flow crosses the volumetric capacity curve of your pump is typically your operating point. It's the design point for the pump, and we come back to that in the second webinar, how to design that. But the point is, in a batch distillation or in a batch dryer, you basically come from atmospheric conditions, and then you just have, let's say, you distill the first light boiling fraction off. And let's say the temperature in your liquid in the reactor determines that pressure. That is the best achievable pressure that you can get, maybe 100 torr. And you can see what's happening at the mass flow, the evaporation rate mass flow at 100 torr is, looking at the vapor state, pressure times volume is constant, is 1/10 of what the vacuum pump supplies at that point at 100 torr. This is where the red arrow going between the mass flow line and the volumetric line. It's actually, the mass flow down there is showing what you actually need in capacity, in volumetric capacity to match the mass flow coming off the reactor. And the top line is actually what the vacuum pump provides. What happens? If you don't control that pump, you have 10 times more capacity on the vacuum pump than the heating power provides in evaporation rate, which means that pump relentlessly evaporates your liquid. And since the heating power doesn't get after it, it cools your liquid down. Your liquid is going down. And that effect, particularly in a drying process, slows your production time down big time. There's a simple fix to it. Control the pump. And in order to control it, you can do throttle control and bypass control. And how that exactly works, we will come back to again in the second webinar. But the whole sense of it, to control a vacuum pump, is actually like the yellow arrow shows, going from the right up to the left, shows you try to mimic the mass flow coming off your reactor. And again, the mass flow is shown here in its volumetric equivalent, and that is obviously pressure related. Again, it's pressure times volume is constant. It's difference between ACFM and SCFM. We're going to come back there, but it is actually your vacuum pump. The controls put your vacuum pump and your heating power means the evaporation rate of your process into an interrelated state where you run at an optimal speed of your distillation and drying time. Everything else, either too low ruins your product because you get it overheated, too high, and you start freezing effect and slow down your production. So controlling the vacuum pump is It's very important. Before we move on to the control point, there's one element to it. Like I said, it's the condenser. If you have a condenser like shown here between your reactor and your vacuum system, you have another vacuum pump acting for you as long as you do the right things. So first of all, the control valve belongs on the inlet of your pump, not close to the reactor and between the reactor and your condenser. If you have the control valve between reactor and condenser as shown here crossed out with the red valve, your vacuum pump would actually make basically pull with this excess capacity that I was talking earlier, pull vacuum on this condenser, what makes the condenser completely inefficient and absolutely impossible to condense anything at that state, again, pressure and temperature. So make sure your control valve is in the right place. And then again, make this condenser in the very first phase of your reaction, where all the vapor is coming off, where your drying goods are really wet and you only want to dry the liquid agent out dry in that wet phase, or in a distillation, on a batch distillation, just get rid of this light boiling fraction as fast as you can. Your condenser is your best friend. Its capacity, again, is the volumetric equivalent to the mass flow that you drain through the drain as a liquid. And it even can be shown, as I tried here in this diagram, in this pressure capacity diagram, it can be shown because it alters the mass flow that is left to be pumped by the vacuum pump itself. So that was about controls. Let's move for a moment into pressure loss. What I've shown is, again, it's just on the icons, it's still the same. It is, the reactor can be a dryer, can be a batch distillation, can be continuous condenser, and the condenser drains into a drain tank in this case, and the vacuum pump is applying vacuum at the drain tank, a very frequently used arrangement for batch distillations. What I also did is, again, I took the same pump than earlier, same diagram, double logarithmic scale. And now in blue is the line that you already know. It's the capacity of the vacuum pump on the inlet of the flange. And in yellow is the capacity of the vacuum pump when you measure it at your reactor outlet. So what you can see is pressure loss in the vacuum industry is really getting interesting below 20 torr. But I just still want to mention that because this interrelation is important. What I frequently hear is, and it's true, it's a density related thing. So mostly we think in gas density and gas friction when we talk about pressure losses. It's gas velocity and density. So the first thought that derives from that is, well, if the gas density is going low, like in a vacuum system, your pressure loss is fine. It's getting lower. That's true until you hit a point where the same idea of going to a low density kicks in with another effect that I wanted to just briefly illustrate to you. So imagine the volume under vacuum, the yellow parts of this diagram is a dust cloud. It's a homogeneous dust cloud with little dust particles flying around. The point is, how do you get basically this dust cloud moving out of the system towards the vacuum pump? If the density of the dust cloud is relatively high, that's fine. It's no problem. The dust in your reactor, in the vapor state in the reactor, would still feel the pull of your vacuum pump when the density is high. But in vacuum, the lower you get into pressure, the less gas density you have. So your dust cloud is basically getting more space, less dense, and all of a sudden, you don't have this interaction anymore of your dust particles in your reactor with your dust particles in the pipe and in the pump. So dust particles in your reactor suddenly don't feel the pull of your pump anymore. And the only way to heal that, when you want to go to pressures below 20 torr, is you need to watch out for pipe diameters put the pump closer to the reactor. Not too many elbows, and certainly, as this is why I chose this example, not a drain from the condenser into the drain tank and then off to the vacuum pump, because that works mostly when you run 50, 100 torque vacuum. But the drain pipe is typically, what, 2-inch? Because it's designed to drain liquid. So your vacuum pump basically pulls vacuum into the reactor through that drain pipe. So you have a two-phase system. So you drain the condenser and you basically pull vacuum through it. Again, doable, but it's a major restriction if you want to get to better vacuum. The other aspect that I wanted to show you when it comes to this drain line is you have a condenser 2-inch drain line into the drain tank and then apply vacuum to it. Is the vacuum pump actually pulls through that pipe, and again, it's if you have all the effects that I was explaining earlier, the vacuum pump eventually just the control valve on the vacuum pump is going to open when you have the set point set for the reactor. So you apply more and more capacity of the vacuum pump to that drain pipe. What happens is you just get the velocity in that 2-inch drain pipe that is too high to have a gas liquid separation anymore. Your drain tank is partly separating liquid from gas, but you start really carrying over liquid into your vacuum pump. And I come back to that, why this is not a good idea. Before I do that, I just want to make you aware of one more point that is that I frequently see, and that is really important. It's the same concept. I just wanted to make you see it and aware of it, and I'm sure you all are. But on the vacuum perspective, it's important. So imagine you have your light boiling fraction is off the reactor on the left. So you're in the distillation, your light boiling fraction has condensed through a condenser or maybe just through the inlet pipe and lands in your drain tank. That's the light boiling fraction, and that is determining now, since that liquid has a temperature and that temperature determines the pressure above the liquid in the vapor. So what your vacuum pump is doing is it's re-evaporating your light boiling fraction. And the best pressure that this vacuum pump now can accomplish is the vapor pressure of your light boiling fraction in the drain tank. Now, your control system is sitting on the reactor, and rightly so demands to support the evaporation rate coming out of the reactor. So your pressure is drifting away. What does the control system do? It basically opens the throttle. It just wants more capacity from your vacuum pump. And all it's getting is a higher evaporation rate from your drain tank, because that light boiling fraction is the best pressure you can accomplish. It's just basically sitting there and is keeping you from getting the capacity that the heating power and the evaporation rate generates from your reactor right now. It's keeping you from getting there. The only way to do this, just keep that in mind. I've seen this a lot, that what's happening is this evaporation rate, since the drain tank is usually not heated, cools the liquid down. It cools it down until it potentially freezes. And then everybody's happy because the pressure is coming gradually down in your reactor. Of course, it's not because your vacuum pump and your control system is opening the capacity. It's solely because the temperature in your drain tank is going down, and therefore the pressure, the vapor pressure of the liquid in the drain tank is coming down. So imagine how much slowdown you have, or let's say it positively, imagine how much capacity and speed in your production you can have is when you say, okay, my light fraction is now gone, my distillation or my drying process slowly moves to lower pressures, just isolate that tank or drain it. Just take the liquid out of the equation, because that's what it's doing. Your vacuum pump is solely busy with re-evaporating your drain tank instead of applying vacuum to your reactor. Very important. I see it very frequently. Here's the effect. If your control system, let's say, has a set point, it has a certain set point, right? Set on the reactor. So you want to have 10 torr on your reactor. That's the set point of the control system, but all you can get is 100 torr because of the liquid sitting there in your drain tank. That's all you can get. Your control system isn't there anymore because the throttle will completely open and give the entire capacity of the vacuum pump available into the reactor. All it does is freezing your drain tank down. It's not working on your reactor. And again, it's kind of misleading because slowly but surely your pressure in your reactor comes down, but it's not because the capacity of your pump. It is because your light boiling fraction liquid is cooling down. Hydraulic locks. Again, this is an easy one, right? Some drain tanks have dipstick drain legs into the reactor for gas liquid separation. That's what they're there for. So make sure that, and I only took this as an example. You might have a siphon somewhere in your inlet pipe where your condensate basically samples, and you just start hydrolocking the system. Again, it's misleading because it's not immediately visible what's going on. Your vacuum pump is pulling on the one side of your siphon or on your drain tank, and in your reactor you basically still have a heating powered evaporation rate that is feeding vapor into your line, into your gas line, into your vapor line, into your inlet line, and where it's eventually condensing, and that condensation effect has a pull. So it's this interrelation where the pressure of your reactor and the vacuum pump's controls, you need to basically just have this sensibility for the balance between the vacuum pumps and the heating pump and what's going on in your reactor. And again, I was putting this presentation together because in the years of experience, I've seen drying processes going from days processing into hours of processing just to have a closer look to these productivity influence, mostly, and how the vacuum pump capacity interacts with your heating power and the process. So before we close this webinar, just briefly, I mentioned it earlier, it is not very good practice to plan and have or allow for a liquid flow, a liquid drain flow into your vacuum pump. I know that liquid drain pumps, for instance, can handle some of it, but it is not very good practice because you can just knock it out. Imagine your vacuum pump is now basically mostly bothering with the liquid and trying to re-evaporate it. So as long as you have liquid phase present, just try to separate it, and once the light boiling fractions are coming off, isolate it, not make it facing the vacuum system anymore. This is the big one. You can imagine liquid drain pumps, again, handle some of it. An oil seal pump or a dry pump don't like that at all. And it's not because they can't stand it mechanically, they can, unless you find yourself changing oil every day, because you have this carryover that is affecting your pump in doing what it's supposed to do. And in this slide, it's just basically just progressing the same effect to the discharge. So imagine you have a reaction going all through the vapor state. Your vacuum pump handles everything that comes in the vapor state, discharges it to the discharge. And at that state, you're basically on the discharge, standard conditions, atmospheric pressure. Typically what was a vapor under vacuum is now turning into a liquid again. So it's condensing. So it's very common that your discharge line is turned into a condenser. If you, so the discharge line should not go just horizontal off and then straight vertical up, because that condensation effect would make the liquid run back into your vacuum pump on the discharge and cause not only trouble, but also the effect of this pump is actually not doing what it's supposed to do. Your vacuum becomes eventually unstable because your vacuum pump is dealing with a liquid phase that a compressor in general shouldn't deal with. Again, mechanically, these pumps can handle it. Just from the processing side, it just simply, again, slows the process down, because this pump, no matter if you turn liquids into the inlet or have discharge condensate running back into your pump, your vacuum pump does not have the capacity that it nominally has, if that wouldn't be the case. So on this last slide, just as a summary on best practices, the big one that I was trying to convey to you is vacuum control. Make sure your vacuum is controlled. Look for the control method and for the control pattern. Keep in mind, if your set point in your reactor, the vacuum control set point, is at a point where just through the liquid states in your reaction and in your system is not achievable, because again, the pressure is not determined by the capacity of your pump, it's determined by the temperature of your liquids. If it's a not achievable process, your control is might as well not present, because the throttle valve will open all the way constantly and cause these effects. So a pressure ramp, as I've shown along the mass flow, just keep that in mind. Are liquids present? Are any tanks left undrained? What's in the tanks? Is it the light boiling fraction? Now you basically have your vacuum system re-evaporating your light boiling fraction. It doesn't do anything on your reactor. Is any liquid, is there a possibility that liquids lock the pipe works? Pressure loss, pipe diameter, again, becomes important below 20 torr, but then it is an effect that is exponential. So if you go to 10 torr or 5 torr or 1 torr, you suddenly see that pressure loss effect that I was explaining as your major impediment to get to that place. Gas liquid separation is always a good idea. Gas velocity, look into separators, and make sure your valves are moving not suddenly. So it's just as a last idea before we close this. If you have a vacuum pump running with a closed inlet, just waiting for the process to get right, and let's say it's a 4 or 6 inch valve, so the vacuum pump basically pulls down to ultimate pressure, whatever that is, depending on the vacuum principle. And we want to go there. We're going to go through that in webinar 3. But it's basically pulled down to as good as it can to the position of the valve. If you open it suddenly, you eventually cause a sonic speed shock wave that goes through your system and causes liquid slugs of a magnitude that can be harmful. Okay, that is it from my side. I wanted to walk you through best practices. In this first place, I just wanted to focus on production capacity or production efficiency, and make you see what's going on, particularly in distillation and drying, and what is basically fundamentally more complicated and different when vacuum systems are being used for handling liquid vapor systems. So thank you.
Thanks, Andreas. I have a few questions that have come in for you, so I'll just start off the top here. The first one, can you please explain the impact of conductance on the performance and essentially the impact on the condenser?
On conductance?
Yes.
Is that a pressure loss thing? I assume it is. So the conductance on the condenser is this. So if I understand the question right, so assume you have a reactor and a condenser close by, and the condenser is under cooling water and the reactor is on a higher temperature. The conductance is simple. Your condenser is basically starting to generate a pressure, a vapor pressure that is on the surface of your condensate. and that creates a pull. And the condenser starts pulling like a pump from your reactor. The conductance for the vacuum pump, so when we talk about the vacuum condensers under very low vacuum pressures, there are certain designs that basically favor the pressure loss aspects on vacuum systems. For instance, it's better to have the agent or the process in the shell instead of in the tubes. Just that's a conductance or a pressure loss item. If you lead it through the tubes, again, if you want to do it at 100 torr, great. If you want to do it at 20, the tubes are becoming a major conductance issue, a problem in pressure loss. I hope that answers the question.
Okay, so the next question is from Kumar. Can we out a vapor balance line between the distillate receiver and the condenser to balance vacuum through a common line? And a follow-up question also, at what temperature should the vacuum trap be set up to have an effective vacuum?
Well, basically the temperature the trap could be set up is anything lower than the temperature of your liquid in your reactor. The lower it is, the more pull you get, because that temperature in your trap is determining the vapor pressure above the liquid phase now, and that is making it a pump. So if you want to have a strong pull from your condenser, I'd say the lower the temperature in your trap, the better, to get that best effect, to get this pull. But when it comes to efficiency of your condenser, that's another aspect. So the cooler your trap or your condenser is, the more condensate you're getting. So the more condensate you're getting, the more vapor you turn into liquid, the less need for a larger vacuum pump. Your condenser is doing all the job. So the quick answer is the lower the temperature in your cooler, the better.
Great. Okay, so another question here from Tim. Could you please explain again why it's better to put the valve between the condenser and the pump rather than between the reactor and the condenser?
Yes, happy to. So imagine you have the valve between the condenser and the reactor. That means, imagine a throttle valve that basically restricts the flow of the vacuum pump's capacity. And the reason is clear: you don't want to have excess capacity of your pump boiling off your liquid too fast, so the heating doesn't come up and it's just slowing your process down like it went through. What happens is your vacuum pump is still, it's a volumetric pump. So your vacuum pump downstream your valve is pulling the vacuum down. Let's say if it has 10 times more capacity than needed, the throttle valve just basically almost closes entirely. So if your reactor is on 100 torr, your vacuum pump pulls down to 10 torr downstream your valve, which means your condenser is now under the same pressure, under 10 torr instead of 100. That changes it, because now you need a real cool temperature. Again, temperature pressure relation. So they are interlocked and in lockstep. So if you lower the pressure to 10 torr, now you need a whole different temperature, much lower, to have a condensation effect at all. So that's what makes your condenser on the downstream of your control valve a slave to your vacuum pump. It's just, your vacuum pump is throttled away, it pulls down. Again, the volumetric capacity is there. It's a volumetric machine. It does everything to get there. So it pulls down eventually 10 times lower pressure, and your condenser is inefficient. It cannot condense at that pressure that the pump generates downstream your valve. And it takes it out of the equation entirely.
Great, thanks. I think we're kind of getting short of time, but I think we can fit maybe one more question in. So this last question, why does the pump productivity drop at low pressure? Should it not be constant across the whole pressure range?
Yeah, the pump productivity is there. It depends on where you measure it. If you measure it constantly on the inlet of your pump, it's always there. It has that performance curve. The pressure loss is actually then measured what is left of your pump capacity or capability on the inlet, what is left on the reactor where you want it, where you need it, and that is the pressure loss that I showed in this curve, where you have actually the original capacity curve on the inlet of the flange. And ANDREAS can simulate your pipes, your pipe work, to basically show you what out of that capacity is left on your reactor where you need it. Okay, so the whole thing is about when you go to a certain pressure and a certain density in your gas press, so the volume under vacuum, you eventually land at the gas density that is so thin that you lose the pull. Basically, the gas molecules in your reactor don't recognize that there is a pump 50 feet away pulling on them. So how do you make these gas clouds, like the example as I used, or the gas molecules move to your pump? It's becoming a coincidental moving effect. So these gas molecules move, and eventually they move towards your pump. But then it's becoming a big issue on how big your restrictions are and all that. So we can simulate that, but what it comes down to is we show both. We show the capacity of the pump that you installed, no matter which one, at the reactor where you need it, and at the pump inlet where it's initially have, let's say, the catalytic curve or the nominal speed. I hope that answers the question.
Great, thanks, Andreas. And thanks everyone for joining today. And just a reminder for people that maybe had some technical issues or weren't able to join, this will be available for download and viewing as well. And you'll get a reminder, an email with a link later today. Thanks everyone.
Thank you. Thank you all for your time listening in. Hope I see you next in 2 weeks for the second webinar. And I hope you enjoyed the first part. Thank you again.